Hello everyone, welcome to the session on communication electronics. In this session, we'll be discussing about the frequency modulation. In this session, initially we will discuss what are the different limitations of amplitude modulation, and then we will go for the introduction of frequency modulation. Also, we will draw the waveforms for frequency modulated signal. So friends, as you know that you are viewing this session on my YouTube channel, Learn with Prakash Kanade, and do not forget to subscribe to the channel. So we have been already discussed in our earlier sessions about the amplitude modulation. We know that in amplitude modulation, the amplitude of the carrier signal is being varied in accordance with the modulating signal. Amplitude modulation is being commercially used in many applications, but you will find that amplitude modulation has several limitations. So initially, we will discuss what are the different limitations in amplitude modulation. You will find that amplitude modulation is not a digital technique. Nowadays, you will find that the digital techniques are more popular, but amplitude modulation is a kind of analog modulation technique. You will find that in amplitude modulation, amplitude of the carrier signal is being varied, and such signal is being transmitted by the transmitter. And therefore, when this signal is received, you will find that most of the time this signal will contain a lot of noise. You will find that the noise gets added into this signal because the noise is also of amplitude varying nature, and therefore our radio receiver cannot separate the noise from the required signal. You will find that many times there are atmospheric disturbances. Say for example, in rainy season, you will find that there are so many disturbances in the atmosphere. Such disturbances are also of amplitude varying nature, and therefore these disturbances are also carried along with the required signal, and therefore these disturbances will make the amplitude modulation reception or AM reception very noisy. You will find that in AM the bandwidth requirement is about the double to that of the modulating signal frequency. So if FM is your highest modulating signal frequency, then the bandwidth in AM must be twice FM. But you will find that practically it is very difficult to keep a large bandwidth for the communication system. You will find that when the AM signal is being transmitted, then the most of the power of the AM signal is being wasted. When we compute the efficiency of the amplitude modulated signal, then you will find that the efficiency of AM is very less, and it is only about 1/3 or 33%. It means that the 2/3 of the power of the transmitter is being wasted, and it is not utilized in carrying the signal. Also, you will find that since the efficiency is less, this signal cannot travel a very long distance. You will find that only up to few kilometers, the amplitude modulated signal can travel on the ground, and therefore the range of the AM radio stations is very limited. Also, you will find that in case of AM, it is not practically possible for us to receive the stereophonic signal. Whenever we hear any music program on the AM radio, then you will find that certain sound is being not heard properly. So this is because you will find that the AM radio station has a limited bandwidth, and because of this limited bandwidth, it is not possible to receive the stereophonic signal whenever the AM systems are used. So you will find that there are several limitations of AM, and maybe because of these limitations, an alternative technique was thought of, and this alternative technique to the AM is being called as the frequency modulation, or FM. Now we will discuss what we mean by FM. You will find that whenever you have any radio receiver, then in the radio receiver, there are two channels present. One is being called as the AM and another is being called as the FM. So you will find that it is possible for you to hear both the radio stations. So you need to adjust the switch accordingly so that you can hear either AM radio station or FM radio station. And the immediate difference that you will find is that the quality of the reception of FM signal is much better than that of the AM signal. So let us understand what we mean by FM. Frequency modulation is also a kind of modulation technique in which the frequency of the carrier signal is changed as per the instantaneous value of the modulating signal. So in frequency modulation, frequency of the carrier is varied, while the amplitude and the phase of the carrier will remain constant. So you will find that the amplitude will not change. In AM, as we have noticed earlier, that is the amplitude of the carrier is being changed. But here the frequency will change and the amplitude will remain constant. And also the phase of the carrier will remain constant. So you can say that the frequency modulation or FM is an alternative technique to that of the AM. So some of the limitations of AM can be recovered in FM. You will find that in FM, the frequency of the carrier is being varied linearly, and this variation is in accordance with the amplitude of the modulating signal. You will find that FM is very popular, and FM is also used commercially in many applications. Say, for example, whenever we want to broadcast the FM radio station, then in that case, you will find that the frequency modulation technique is used. Also, you will find that whenever we hear our TV sound, then for the transmission of the TV sound, you will find that the frequency modulation technique is used. Also, in many other applications, such as in radar systems also, you will find that the frequency modulation technique is used. Frequency modulation technique is not a new technique, it is an older one. You will find that the first practical FM system was prepared in 1936 only. The frequency range that is being used in FM is from 88 megahertz to 108 megahertz. So the frequency that is being used for FM is much higher than that of the AM. You will find that the bandwidth requirement for the FM radio is about 15 kilohertz. So this bandwidth requirement is higher and it can be achieved because the frequency range that is being used for the FM is higher, and therefore it is possible for us to keep the higher bandwidth for FM radio. Now we will see what is the theory of frequency modulation. You will find that in frequency modulation, the frequency of the carrier is to be varied, and this variation is proportional to the instantaneous value of the modulating signal. So this is a block diagram for frequency modulation. You will find that in the frequency modulation, we will apply the modulating signal. Also, we will apply the carrier signal, and at the output, the modulated signal, that is the FM signal, will be generated. You will find that there is a change in the carrier frequency, and this change in the carrier frequency is in accordance with the amplitude of the modulating signal. And this change in the carrier frequency is being called as the frequency deviation. So you will find that in FM, there is some center carrier frequency, and there will be a change in the carrier frequency in accordance with the amplitude of the modulating signal. So the frequency of the carrier signal continuously goes on changing as per the amplitude of the modulating signal. And this change in the frequency of the carrier signal is being called as the frequency deviation. You will find that there are basically two types of FM. The first type is being called as a narrow band FM or NBFM, and the another is being called as a wide band FM or WBFM. You will find that in the narrow band FM, the frequency deviation is low. So as I told you that there is a change in the carrier frequency according to the value of the modulating signal. When this frequency deviation is low, then the type of the FM is being called as a narrow band FM. And when the frequency deviation is much higher, then the type of the FM is called as the wideband FM. You will find that narrow band FM is being used in certain FM systems. Say, for example, in walkie-talkie or in two-way radio systems, you will find that the narrow band FM is being used. Wideband FM is preferred whenever we want to transmit the high quality audio. So whenever a stereophonic sound is being transmitted and you are expected to receive a stereophonic sound, then in such a case, you will find that the wideband FM technique is being used. Now we can draw the FM waveforms. As shown in this diagram, you will find that the first signal is a modulating signal. This signal is a low frequency signal, and you will find that it can be a sinusoidal signal or it can be a non-sinusoidal signal also. So you will find that the amplitude of this modulating signal is continuously changing. Now this second wave represents the high frequency carrier wave. So you will find that the number of the cycles of the carrier signal are much higher than that of the modulating signal. And the third wave will represent the frequency modulated signal. So you can easily observe that as the amplitude of the modulating signal goes on increasing, then you will find that the frequency of the FM signal also goes on increasing. And therefore you will find that here we will observe a kind of compression. That is, there are more cycles in a short span. And as the amplitude of the modulating signal goes on decreasing, then you will find that the frequency of the FM signal also goes on decreasing. And therefore you will find that there is a kind of separation between the cycles of the FM signal. That is, you will find that here it is a compression, while here it is a separation. That is, there is a wider gap between the two cycles of the FM signal. So here you can easily observe that there is a continuous variation in the frequency of the FM signal, and this variation is proportional to that of the amplitude of the modulating signal. Here also you will observe that the amplitude of the FM signal remains constant. In AM, we have seen that the amplitude continuously goes on changing. But in FM, you will find that the amplitude will remain constant while there is change in the frequency. That is, sometimes we'll get more number of cycles, sometimes we will get less number of cycles of the FM signal. So there is a continuous change in the frequency of the FM signal. And this change is as per the instantaneous value of the modulating signal. Now we will demonstrate it more. As shown in this diagram, suppose this is our modulating signal, which is a sinusoidal signal. And in order to illustrate it, what I have done is that I have marked different positions by the points. So this is A point, B point, C point, D point, and E point. So you will find that from this waveform, at the points A, C, and E. So this point A, then this point C, and this point E. All these 3 points are on the x-axis, and you will find at these points, the value of the modulating signal is 0. And therefore, you will find that at these points, there will be no change in the frequency of the carrier signal. That is, the frequency of the FM signal will be same to that of the central carrier frequency. So at this point, there will be no change in the frequency. Now, when we go from A to B, then you will find that the amplitude of the modulating signal goes on increasing positively. Now at point B, you will find that the amplitude of the modulating signal is positive maximum. And therefore, when the amplitude goes on increasing from A to B, you will find that the frequency of FM signal also goes on increasing. And at point B, you will find that the modulating signal amplitude is maximum. And therefore, the frequency of FM signal is also maximum at the point B. Now, from B to D, you will find that the amplitude of the modulating signal goes on decreasing, and therefore the frequency of FM signal also goes on decreasing from point B to D. So you will find that at C, the amplitude of modulating signal is almost 0, but from C to D, it increases negatively, and therefore the frequency of the FM signal also goes on decreasing. At point D in this waveform, you will find that the amplitude of the modulating signal is maximum negative. And therefore, at this point, the frequency of the FM signal is minimum. So you will find that a large compression is being observed at point B, while there is a large separation between the cycles of the FM signal at point D. You will further find that when the modulating signal travels from D to E, then its amplitude again increases positively. And at E, it becomes equal to the center frequency. And therefore, you will find that the amplitude, as it goes on increasing, then the frequency of the FM signal also goes on increasing. and at point E, it becomes equal to the central frequency. So hopefully, friends, you have understood this concept of frequency modulation, and hopefully you have understood what we mean by FM, the limitations of AM, and how to draw the FM waveforms. In our next session, we'll be discussing about the deviation ratio and the modulation index in FM. Thank you, friends, for viewing the session. And if you have any queries regarding this session, then you can ask it to me, or you can ask it in oral discussions. Thank you for viewing the session.